This example gives us a yo-yo. So imagine that this is a string. It's held fixed either by your hand or it's tied to the ceiling or whatever, and the string is wrapped around this object so that when we let it go, this unwinds and rolls and falls down like a yo-yo would. The yo-yo has a mass, capital M, and radius r, and its moment of inertia about its center of mass, about at this point right here, is c times mr squared. That c is a constant that tells you how the mass is distributed in the object. If this is a solid disk, like a hockey puck, c would be 1/2. If it's a ring, where all the mass is on the outside, like a hoop, c would equal 1. So we'll leave it general, c times mr squared, so that as we solve this problem, we can see how that factor propagates through the solution and shows up in the answer. What we're supposed to find here is the yo-yo's acceleration a as it unwinds this way and falls this way. I'm going to solve this problem 3 different ways. The first 2 will use Newton's laws, and the third will involve work and energy. Each method has its own advantage, and each has particular things that we need to watch out for and be very careful with. I'll point all of those out along the way. All right, the first 2 methods involve Newton's second law. So for that, we need to start with a free body diagram. Let's draw a free body diagram of this yo-yo. There's its center. Here's the yo-yo, and there are 2 forces acting on it. The yo-yo's weight acts at its center of mass, capital M times G, and there's a tension pulling up on this side. Notice that I've drawn the object with size and shape, and I've shown where the forces are acting. I've done that because in a minute we're going to sum torques on the yo-yo. And before you can sum the torques on an object, you need to account for the location on the object where that force acts. So when you draw a free body diagram intending to sum torques later, you need to draw it with size and shape and show where on the object the force acts. That will let you calculate torques later on. We have 2 Newton's laws that we're going to write down and use first. First, we can sum forces in the vertical direction and set it equal to mass times acceleration in that direction. And then we can sum torques and set it equal to the moment of inertia times alpha. We need to pick a coordinate system. And here is a place where we have to be very careful. Notice that there are 2 accelerations here. There's the translational acceleration, and that is the acceleration of this yo-yo's center of mass as it falls. And there's this angular acceleration. That is telling you how the angular rotation is changing as it falls. It's spinning faster and faster and faster, and as that happens, it falls faster and faster. This A and this alpha are related, in this case by the no-slip condition. This yo-yo is rolling without slipping on this string as it unwinds and falls. That means the tangential acceleration equals r times alpha. Now we're going to treat these as signed quantities. I want to make sure that a positive alpha corresponds to a positive acceleration. So I'm going to choose my coordinate systems so that if alpha is positive, the acceleration a is also positive. So let's think about alpha first. Alpha tells me how this rotational rate is changing. As the yo-yo rotates this way, it's going to move down. So I'm going to let both of those be the positive direction. For alpha, I'm going to let the positive direction be this way. I'll draw that right here. So counterclockwise rotations in alpha are going to correspond to a positive acceleration. So for A, we're going to let down be positive. That way, positive alpha corresponds to positive acceleration, and I can write that A equals R alpha. That's the link between this translational acceleration and this rotational acceleration. Be careful of this. If you let A be positive upwards, then these two are related with a negative sign. So A would equal minus R alpha. If A is positive up, and alpha is positive this way. So be careful if you want to write this, you make sure that the rotational motion and the translational motion have the same sign. Okay, with that, we can jump into Newton's second laws. The first one tells me to add up all the forces in the y direction. Well, y is positive down. This is our positive y direction. So that means that mg minus t equals the yo-yo's mass times its acceleration. I have two unknowns here. I don't know the tension, and I don't know the acceleration. So I need another equation. That's going to be this one. Before I can calculate torques, I need to know the axis that I'm going to sum the torques about. We'll choose here the center of mass. So we'll sum torques about that point. On our free body diagram, that's right here. I'm going to sum torques about the center of mass. Here's an important thing. That means I need to calculate moments of inertia about the same point. Those 2 points have to be the same. And my positive direction is given right here. So I'm going to sum torques positive in the counterclockwise direction. All right, there are two forces, but one of them acts through the point where I'm summing torques. So it doesn't give me any torque. No torque due to the weight about that point. The only other force is the tension, and it has this moment arm, the radius r, so that the torque has a magnitude of the moment arm times the force, and we see that it's in the positive direction. Using the right hand rule, you put your right hand fingers this way, curl them towards the force, and your thumb points out towards you as your right hand fingers curl in the counterclockwise direction around it. That's our positive direction. And it equals the moment of inertia about the center of mass times alpha. Now alpha is related to the translational acceleration a. From down here, I can rewrite alpha as a over r. This a is the same as this a, because we've been careful with our signs. The reason for writing it this way is that if we left an alpha in there, we would introduce yet another unknown we would have to eliminate. So we replace it with a over r. So let's simplify this. This r, cancel those r's, and I can solve for the tension T. It equals C times ma. I now have two equations for two unknowns, the tension and the acceleration. So let me take this expression for T, substitute it into here, and solve for the yo-yo's acceleration. Here's how it goes. mg minus the tension equals ma. Cancel all the m's and move this term over to find that the acceleration is g over 1 plus c. All right, notice that it's positive, which tells me that the yo-yo is going to accelerate down in our positive direction. And it's interesting to see that it doesn't depend on the yo-yo's mass or the yo-yo's size. All it depends on is g and this constant c that tells us how the mass is distributed in the yo-yo. As c gets bigger, as the mass moves to the outside, and this yo-yo becomes more hoop-like or ring-like, the acceleration goes down. So as the mass moves out, this yo-yo will accelerate more slowly. If the yo-yo was in the shape of a hockey puck, a solid disc, c would be 1/2, and the acceleration would end up being 2/3 of g. If the yo-yo was in the shape of a ring, hoop, then c would equal 1, and the acceleration is reduced to 1/2 of g. So that's one way to solve this. Let's look at another way. What I'm going to do next is change the pivot. I'm going to change the point that I sum torques about. In the case we just solved, we had the pivot right here. What I'm going to do is move it over here and do this problem again and show you an advantage of that and point out something that you have to be careful with. Okay, so let's call this point A and redo this problem, summing torques about that point. I'm going to erase this stuff over here that is going to change, and instead of summing torques about the center of mass, we're going to sum torques about what we're calling point A. But nothing else changes. This is still our positive direction for torque and rotations, and down is still our positive y direction. Now, as it'll turn out, I won't even need the translational equation in this case. That's the advantage. And the reason I'm not going to need that is because when I sum torques about point A, there's only going to be one torque, and it's going to be the torque due to the weight. This torque due to the tension is going to be 0 because it acts through the pivot. So the advantage of putting the pivot here is that this unknown force, this tension, gives us no torque and is not going to show up. That will allow us to solve this whole problem just using this equation. Here's how it goes. We need to add up the torques on this object, and we see that there is only one. It is the torque due to the weight. Our pivot is now here, so the r vector goes from the pivot to the point where the force is applied. So the r vector now goes this way, and the right-hand rule tells me that the torque is in the direction of r crossed into the force. So your right-hand fingers go this way, they curl down towards the force, which is the weight, and your right-hand thumb points out towards you, with your right-hand fingers curling this way in the positive direction. So that torque is positive, and it has a magnitude equal to the moment arm times the force. And that's going to equal the moment of inertia times alpha. Now here's the tricky thing to watch out for in this method. This is the moment of inertia of the yo-yo about this point. What we were given is the moment of inertia about the center of mass. So I need to take this moment of inertia and use the parallel axis theorem to write the moment of inertia about that point. So we get moment of inertia about the center of mass plus the mass times how far we moved the axis squared. And I still have to multiply by alpha. I moved the axis from here, from the center of mass, to this point. I moved in a distance r. So we pick up an m d squared, where d equals r. Alright, again I have this alpha, which I want to eliminate using my rolling without slipping condition. So I'm going to get rid of that, and in its place I'm going to put a over r. And now we can solve for the acceleration. What happens is the mass cancels from every term. This r and this r cancel those r's, and I find that g equals, if I turn this around, 1 plus c times a, so that a equals g over 1 plus c, just like it did last time. The advantage to this method is that you can solve the whole problem with one equation. There's only one unknown. The tricky thing to watch out for is the moment of inertia about this point needs to be gotten using the parallel axis theorem. Alright, so that's two methods. Let me show you one more using work and energy. We won't need the free body diagram or Newton's laws. So let's get rid of all this. And as it turns out, we won't need this no-slip condition on acceleration. What we will need, though, is the no-slip condition on the velocity, which tells us that the tangential velocity is r times omega, and we'll need the work-energy equation. The work done by other forces that we have no potential for equals the sum of the mechanical energies, kinetic plus potential, equaling the sum of the kinetic and potential energies at the end of the motion. Alright, now two things. The same discussion about signs applies here. If it's rotating this way, that's going to be our positive omega, and down is going to be our positive velocity. So that V is going to equal R omega, with that being positive rotations and that being positive translations. There are no other forces doing work on this object. We'll assume that the yo-yo starts from rest up here, and then it rotates and falls. I'm going to assume that the yo-yo translates and falls through some height h, so that at the end the yo-yo center of mass ends up here, and it's right there moving down with some velocity v. If we set y equals 0 right here, that means at the initial point, way up here, the potential energy is mg times h. The yo-yo's final kinetic energy down here is due to both its translation of its center of mass and its rotation about its center of mass. So there's its final kinetic energy, translation of the center of mass plus rotation about the center of mass is equivalent to rolling without slipping. The final potential energy is 0 because it's down here where y equals 0. All right, so what we're going to do here is solve this expression for the velocity v at the bottom and then use kinematics to find its acceleration. The next step is to replace the moment of inertia with the expression that we have and to get rid of omega in favor of v using the no-slip condition. Looks like this. Here's the moment of inertia about the center of mass, and omega is v over r. We can now cancel the mass. This r squared cancels that r squared, and I can multiply everything by 2 to get rid of these pesky 1/2. That tells me that 2gh equals, factoring out a v squared, 1 plus c. Or v squared is 2gh over 1 plus c. Now what we found here is the yo-yo's speed, really the square of its speed, at the bottom. But what we want to know is its acceleration. So the yo-yo fell through a distance h at constant acceleration, acquiring this final velocity squared. We'll find the acceleration using kinematics. The time-independent kinematic equation tells me that vy squared is v naught y squared plus 2a delta y. Now vy squared is the final y component of velocity. That's this guy right here. 2gh over 1 plus c equals the initial, that's 0, started from rest, plus 2 times the acceleration we want times the displacement, delta y. That equals h. It's positive because it's going down in our positive direction. Cancel the h and cancel the 2 to find the acceleration equals g over 1 plus c, the same answer we got before. So that's how you can solve the yo-yo problem 3 different ways. In general, you can use any of these 3 methods on these rotational dynamics problems. I hope that was helpful, and I'll see you in the next one.